Hello, today we will discuss about metal oxide semiconductor field effect transistors. I will cover the structure, working principle, transfer characteristic of MOSFET. I will also discuss the CMOS. We have discussed about the transistors, but why MOSFET? If you see the power consumption compared to the other transistors, bipolar junction transistor, junction field effect transistor, in MOSFET the power consumption is low. Second, the size of this transistor is very small, so we can fabricate the more number of transistor on same wafer. Fabrication cost is low compared to other transistors. MOSFET is the prime building block for CMOS digital logic circuits, and we can use these MOSFETs in microprocessor, memories and power devices. So, here on the screen you can see the structure of metal oxide semiconductor field effect transistors. So, we have two terminal here, source and drain. Our substrate is P type and source and drains are made by the highly doped N type, and gate is in between source and drain, and on the top of this P substrate we have one thin oxide layer, and on the top we have the metal. So, we can say this one, the heart of this device is the MOS diode here. So, initially if you will not apply any bias on the gate, in that case we have two here junctions, one is N plus P and another one is P N plus. So, if you will apply here negative bias on the source and positive bias on the drain, now our one junction is in reverse bias. So, there is no current flow from source to drain. The current flow is only due to the leakage current, and this current is very small. Now, if you will apply some bias on the gate, if you will apply the positive bias here, so the negative charges will generate on the surface, on the semiconductor surface here, and if you will apply the sufficiently bias above the threshold voltage, in that case one electron layer will generate on the top of this P substrate, and now through these layers we can connect from the source to drain. So, the current flow is there, this one is will be very high. So, by using this gate voltage we can tune the current between source and drain. So, the conductance of channel can be modulated by varying the gate voltage, and this conductance is affecting the output characteristics, that one is our drain current. So, first we will calculate the threshold voltage, how much voltage we have to apply to generate these carriers on the surface. So, here you can see the case, in this one we have applied the sufficient voltage, and this voltage is inverted our semiconductor surface. So, our semiconductor is P type. So, if you will apply the positive bias on the metal, this positive bias will generate the negative charges on the surface, and if this voltage is above the threshold voltage, this will generate a inversion region on the surface. So, we can connect our source and drain through this inversion region. So, the applied voltage will appear here partially on the oxide and partially on the semiconductor. So, suppose we have applied V voltage, here in the equation you can see this one partially V0 voltage will appear on the oxide and psi S will appear on the semiconductor. Psi S is the, here is the surface electrostatic potential. So, basically the surface electrostatic potential will change, this one is depend on the applied voltage, how much voltage we have applied. So, initially our Fermi level of semiconductor and metal both in the same energy level. So, here the psi S is there, this one is 0, but when we have applied this one, here the surface potential will come psi S and V0 voltage will here will appear on the oxide. So, now the V0 we can calculate, V0 equal to E0D, E0 is the electric field inside the oxide layer, and this we can calculate from the charge. Qs is the generated charges in the semiconductor. So, our applied voltage here across the oxide V0 we can write Qs upon C0. Here we can write this one, our applied voltage here V equal to Q Na W upon C0. This one is the total charges, because total charges in the semiconductor in the depletion region we can take this one is the Q Na and W is the this one depletion width. So, total charges is Q Na W and C0 is the capacitance of this oxide layer, and the psi s here we have defined previously, this one is Q Na W square upon 2 E s. If we will solve this equation, we will get the depletion width W equal to epsilon s upon C0 and square root of 1 plus 2 V C0 square upon Q Na epsilon s minus 1. So, by using this equation we can calculate the depletion width. Now, if we see the capacitance, here we have two capacitance, one is due to the oxide layer, another one is due to the junction here, and here junction capacitance is depending on the gate voltage, and both these capacitance are connected in series. So, overall capacitance of our device we can write C equal to C0 Cj upon C0 plus Cj. Here you can see on the screen this one, and the junction capacitance is Cj equal to epsilon s upon W. This one is similar to the PN junction, and here we are taking the cross section area unit. So, now we can write, if we will substitute here the depletion width we have derived, and if we will substitute these values depletion width in here in the capacitance, we get this one C equal to C0 equal to 1 upon square root of 1 plus 2 epsilon Ox square upon V upon Q Na epsilon s d square. Here epsilon Ox is the permittivity of oxide layer. So, now here if we will increase the voltage, what will happen? Our capacitance will decrease. So, when the applied voltage is negative, then there is no depletion region. So, in that case our capacitance of device is equal to C equal to C0 and Cj will be 0. Now, if we will apply the sufficient here voltage on the gate, this one threshold voltage, so we got the strong inversion in the semiconductor. So, this we can write here Vt equal to Q Na Wm upon C0, and now our surface potential is equal to the inverted this one psi s inverted, and if we will substitute the maximum depletion width, we will get this equation here square root of 2 epsilon s Q Na 2 psi b upon C0 plus 2 psi b. So, if you will apply this threshold voltage, now our surface is in strong inversion region, and one this electron layer is created on the surface. So, in this case the here capacitance will be the minimum. So, C minimum equal to epsilon Ox d plus epsilon Ox upon epsilon s Wm. So, by using this one we can calculate the capacitance, and here in the figure you can see when we have applied the negative bias, capacitance is very high this one, and this one is equal to the oxide capacitance, and when we have applied the threshold voltage, this capacitance will decrease and will reach in the minimum position. So, here by extrapolating these lines the minimum, and from this low we can define the threshold voltage, and by using this equation we can calculate the threshold voltage. So, our device is on when we have applied the threshold voltage, otherwise there is no inversion layer, there is no electron layer, and there is no conduction between the source and drain. So, now we will come on the operation of MOSFET. So, here we have applied the sufficient voltage, and now our gate voltage is greater than the threshold voltage. So, already here the channel is formed between the source and drain. So, if our drain voltage is low, initially this current will increase linearly, follow the Ohm's law, V equal to IR, and we can see the depletion region. So, here the depletion region from source to drain, this one is almost uniform at the low voltage, but if we will increase the voltage, here depletion region is there, this will increase and this will suppress the channel near to the drain. So, now here we will reach near to the this one pinch off point. So, at the pinch off point there is no channel at the drain side, only channel is in source side, but here this one is in the minimum position. So, now our current is there, this will saturate, and this current is called the saturation current, and voltage is the VD saturation voltage. Now, if we will increase the drain voltage, here the current will not increase, this will be the constant. So, here in figure A, B and C you can see the low drain voltage, near saturation and beyond saturation. So, beyond this saturation our depletion region is very high, and this one is suppressing our channel. So, now we will come on the MOSFET characteristics, how our output characteristic is depending on the gate voltage. So, here we will derive the relationship between output current ID, VD and VG. So, here we will consider the ideal MOSFET. When we are talking about the ideal MOSFET, that means the gate structure corresponding to a ideal MOS diode, only drift current is considered, carrier mobility in the inversion layer is constant, doping in the channel is uniform, reverse leakage current is negligible small, the transverse field created by the gate voltage in the channel is much larger than the longitudinal field created by the drain voltage. The charge contained in the surface depletion region of the substrate are induced solely from the field created by the gate voltage. Here in the figure you can see the MOSFET, this one is operated in the linear region. So, we have applied the low voltage here, the channel is formed. So, our gate voltage is greater than the VT, our threshold voltage. So, already we have discussed the gate voltage Vg equal to V0 plus psi s, and V0 here the voltage appeared on the gate oxide, we can calculate, this one is the total charge upon capacitance. Now, we have to calculate this total charge, how much is the total charge. So, the total charge induced in the semiconductor per unit area Qs at a distance y from the source, we can calculate here Qs this by using these equations, minus Vg minus psi s y into C0. So, by using this equation we can calculate the here total charges induced. Qs is the total charges in the semiconductor. Now, here we want to calculate the charges due to electrons. So, we want to calculate the charges inside the inversion layer. So, this one Q and Y we can define total charge minus this one is in the depletion region charge, and here we can substitute these values here Q, this one is Qs already we have calculated, this one is minus Vg minus psi s y C0 minus Qsc. So, Qsc is the charges in the depletion region. So, here charges in the depletion region, because our depletion region in the strong inversion case already this one is reached at the maximum position. So, by using this equation we can calculate here the charges in depletion region equal to minus Q Na Wn, and here the maximum depletion width we have derived this one, we can substitute in this equation, and by using this one we can calculate the charges in the inversion layer per unit area, this one is the Qn at the y position. Now, we want to calculate the conductivity of the channel. So, conductivity here sigma is depending on Q and carrier concentration and mobility. This equation in the initial lecture we have derived sigma equal to Q n mu n. So, now if we will calculate the conductance, this one conductance of channel G equal to sigma A L, and if we will substitute here conductivity and all these values, we will get this one G equal to Z is the cross section width Z upon L 0 to xi. If we will integrate this one sigma x dx, we will get this integration is the total charges Qn. So, now our conductance G equal to Z mu n L upon total charges Qn. The channel resistance of an element section dy we can calculate dr equal to dy upon channel conductance G and width L, and if we will substitute here conductance value, we will get dy upon Z mu n and the total charges Qn in the inversion layer. So, now the voltage drop across the element section, we can write this one dV equal to id dr, and if we will substitute here the value of dr, we will get the voltage drop across this element dV equal to I dy upon Z mu 1 and the total charges in the inversion layer. Now, if we will integrate this equation from y equal to 0 at the source, y equal to 0 and applied voltage is 0, to drain y equal to L and applied voltage at the drain is Vd. If you will calculate this one, here we will get the drain voltage. So, drain voltage here, this one is depending on the gate voltage, also on the drain voltage. So, by using this equation we can calculate our output characteristics here. If we will plot this one, here you can see the here ID Vd plot here. So, when we are here, this one is the voltage Vg minus Vt. When we are changing the gate voltage, here if you see our saturation current is also changing. So, here we have one is the linear region, another one is the saturation region, and this one is the pinch off region. Yeah, you can say this one is the here our current will saturate. Now, in the linear region we can use the approximation because our Vd is very small. So, here we can write our drain current Id equal to Z upon L mu n C0 Vg minus Vt into Vd. Here this approximation is valid when Vd is very small than Vg minus Vt, where Vt is the threshold voltage. Already we have calculated this one. Now, one more parameter we can define here, how much is the channel conductance Gd. This one is the, here we can define one more parameter, that one is called the channel conductance Gd. This one is dId upon dVd at the Vg constant value, and this will come Z upon L mu 1 C0 Vg minus Vt. And the another important parameter is the transconductance, how our drain current is changing with the gate voltage. This one is called the transconductance Gm equal to dId upon del Vg, and here this one is depend on Z upon L mu and C0 Vd. So, these are the parameter in the linear region. So, in saturation current our drain current is constant, and if you will take the derivative with respect to the drain voltage, this will be 0. So, the channel conductance in saturation region is 0, and in transconductance we can calculate for this one Id saturation is Z upon 2L mu n C0 Vg minus Vt square. So, now by taking the derivative with respect to gate voltage, we can calculate the transconductance, and this one will come Gm equal to Z upon L mu n C0 Vg minus Vt. So, now I will come on the type of MOSFET. So, here we can divide broadly in two categories. First one is the depletion region. Yeah, this one is also called the on state. So, in the on state, the channel is formed between the source and drain, and the second case is enhancement mode. In this one is also called the off state. So, there is no channel between source and drain, and the resistance is very high between source and drain because channel is not formed. So, here you can see this one different type of MOSFET. So, here you can see the different modes. The first one is N channel enhancement mode. This one is normally off, there is no channel between source and drain. So, now if you will apply the voltage, positive voltage, the here the inversion layer, the electron layer will generate this one, and here you can see the output characteristic, how drain current is changing with Vd and Vg, and we can define here the transfer function in the right hand side you can see. So, initially when we have not applied any gate bias, this one is in off state, and now if you will apply the threshold voltage, this will come in the on state. So, we have to apply some threshold voltage Vth. Initially if you have not applied any gate bias, this transistor is in off state. So, here you can see the transfer characteristics, and because between the source and drain, here channel is electron channel. So, we call this one is N MOSFET, and if channel is forming the holes, then this one is called the P MOSFET. So, here in the second case, now the channel is formed, we have applied some positive bias here. So, now the channel is formed, this one is called the N channel depletion, So, normally this one is the on state, and to bring this one in the off state, again we have to apply some bias. So, you can see the transfer characteristics. Third one is the p channel enhancement. So, here the channel is forming, substrate is n type semiconductor and channel is forming the holes channel. So, this one is called the p channel. Again here also we have two mode, normally off, normally on. So, when channel is forming, this one is normally on, and if channel is not forming, this one is the normally off. So, basically here this one is depending on the channel. We can divide in two category, enhancement mode, depletion mode. If channel is not forming, our transistor is in enhancement mode. If channel is forming, then our transistor is in depletion mode. So, in the right hand side you can see the transfer characteristic. This one is the characteristic between output current and our input gate voltage. So, if our transistor is on state, we have to bring in off state, we have to apply some voltage, and if transistor is in off state, again to apply in the on state, we have to apply some voltage. So, now I will come on the complementary metal oxide semiconductor. This one is the CMOS. So, basically CMOS is the combination of NMOS and PMOS. So, NMOS, in the NMOS we have to fabricate on P substrate, and here channel is the electron channel. In PMOS, channel is the hole channel. So, here you can see if you will fabricate both together on a same device, and now if you will apply the biasing here, in the below you can see the circuit diagram. So, in this one we have one PMOS and another one is the NMOS. Now, this CMOS, basically this will act as a NOT gate. So, if you will apply here the some digital signal 1, some voltage, our output will be 0. If you will apply 0 voltage, our output will be the maximum. So, here we can use this CMOS for the digital logic applications. If you will apply V in 1, that means if you will apply above the threshold voltage here, now our here the second transistor is there, NMOS, this will come in the conducting state and our output current will be 0. In another case, if we will apply 0, negative gate turns PMOS on and our output will come 1. In today's lecture, we have discussed about the working principle, structure and type of metal oxide semiconductor field effect transistor. We have derived the threshold voltage and transfer characteristic of MOSFET. We have also discussed about the structure and working principle of CMOS. I hope you have enjoyed the lecture. Thank you very much.